Okay, here's just a quick video. In yesterday's class we were talking a little bit about a circle, and if you have a circle, I know there's some well-drawn circles here on the screen, but I'm going to draw a bad one. And you take a diameter of that circle and you come across here. Any time that you go from one edge of the diameter to the other, this angle here ends up being a right angle. So it doesn't matter which circle I draw and which diameter I draw. If I connect the edges of the diameter with one spot on the circle, I always end up with a right angle. So in a better drawing, this animated one here shows point B moving around the edge of the circle, and the angle that's following along here, the angle ABC, is always going to be a right angle. So it doesn't matter if it's way off to the side. I'm just going to get rid of this animated one. It's a little bit distracting right now. It doesn't matter if it's way off to the side or straight up in the middle. So in this case, like example A or B or C, it doesn't matter where we hit the circle. If we have a circle and we draw a line from one edge to the other, this is a diameter across the circle, we always get a 90-degree angle in here. So why is that always the case? There's a really quick explanation, or a more in-depth one. I'll give you a quick one. If this is the center of the circle, which it is, then the distance between here, O to C, is a radius. The distance between O to B, from the center of the circle to an edge, has to be a radius as well. That makes this circle here, or sorry, this triangle here, so the triangle that I'm going to do all in blue, that makes this isosceles. And for any isosceles triangle, the two angles at the base are always going to be equal to each other. It doesn't matter the shape of the isosceles triangle, but if it is isosceles, these two angles at the base are going to be identical. So that's what we've got going on there. This is the two identical ones, so these two angles here, labeled angle beta in this case, are the same. If we look at the same deal on the left-hand side of the circle, the distance between A, the edge of the circle, and the center, that's a radius. And the distance between O and B is also a radius. So that means that this is also, this green triangle, also isosceles, which means that these two angles here are always going to be equal to each other. Now they might be this angle here, and, well, this one isn't a radius. Hang on, bad example. They might be, if I draw another circle, something like this. And then in this case, so if we've got our bit in the center there, this angle and this angle are the same, or this angle and that angle are the same. They might be really close to each other, or they might be, if we have our diameter, it might be like a point way over here. Imagine that's a straight line. If we draw a line right to the center here, then our two angles here and here would be identical, or our angles here and here would be identical. It doesn't matter where on the circle we choose to draw it. The fact that it's an isosceles triangle is just a result of this being the center of the circle, and if we draw a line to that imaginary point, we get a radius and a radius. So all of these yellow lines here are radii, which means they're all the same length as each other. So if we look at that again, we know for any triangle, the sum of all the angles is 180 degrees. We know that. In this big triangle, I'm going to highlight it maybe here in, yeah, yellow's fine. The big triangle, we know that those angles all have to add up to 180. And we also know that for the green triangle, they have to add up to 180. And for the blue triangle, they have to add up to 180. So if we look at just that big triangle, so just the one I'm going to highlight here in yellow, we've got, so they have to add up to 180, but we've got an angle alpha, that's this letter right here, another one right here, alpha and alpha. And we've got beta and beta. Why not A and B? I don't know, that's just a picture that I pulled up. So alpha and beta together have to, so this angle, this big angle, which is an alpha and a beta, and this one here, all of those together have to work out to one full triangle. That's 2 of those alpha angles from the green triangle, and 2 of those beta angles from the whatever color it used to be, blue triangle, equals 180. If I were to divide both of these by 2, because there's a common factor I could pull out of here, so the 2's will cancel, and here the 180 divided by 2 will be 90. So we just get 1 of these alphas and 1 of these betas together equals 90. Just going to show this one step one other way. So if we have 2 alpha plus 2 betas equals 180, we could rewrite this as 2 times alpha plus beta in brackets, and you'd have to distribute that out if you wanted to actually figure that out. And in that case, when we divide by 2, it might be more obvious that that's alpha plus beta, just 1 of each. So 1 of these angles here that were initially in green, and 1 of these angles here that were initially in blue equals 90. But if we look, what do we got here? Across this angle, which I claimed at the beginning was always going to be 90, always going to be 90, always going to be 90, it's 1 of these and 1 of those, 1 alpha and 1 beta. Always going to be the case. So that angle there is the red angle in the picture, and it always got to be 90 degrees. Anyway, in case you're interested, there you go. If you're not interested, you probably didn't watch the video. So I think it works out for everybody. This is called, I didn't come up with this, neither did anybody in this century or even this millennium. This is his Thales, or sometimes we pronounce it Thales, but I don't know why. I think it's actually a Thales theorem. It's got a few. If you read about this guy, he's from a place called Miletus. Used to think the whole world was made of water. He's an interesting fella. You want to read about him, you could. If you want to read more about it, that's what to search for. All right. Hope that helps, or else wasn't too annoying.